All right, so good afternoon, friends, family, and random internet strangers, and welcome to week 9 of Let's Read Code. So today is going to be a very quick trip through the last couple chapters in the book, which really get out of the details and all of the intricate little bits of how computers work and are more about um, some of the things that have happened to make modern computing work the way it does at a higher level. So we're going to jump in here. Did I get my thing back? There we go. Great. So starting with chapter 20, talking about how computers represent text, which is kind of important because that's most of what computing seems to be used for anymore. Passing text around and communicating with people. Spends a lot of the chapter talking about sort of old school text representation methods. Really, I want to talk more about ASCII, which is sort of the underlying thing that set up how modern computers work with text. So the original ASCII specification, each character is 7 bits. So that leaves us with 128 different characters or letters or numbers or symbols or whatever that we can play with, right? The first 32 characters there aren't really what we call printable characters, what we call control characters. Most of those originated from the days of the teletypewriter. So this was a thing that sort of followed after the telegraph. So rather than someone having to sit and punch in Morse code very, very carefully, basically hooked up a keyboard to a line that went somewhere else that was hooked up to basically a typewriter printer kind of deal. So I could sit here on my end with my teletypewriter and punch in my message on a regular keyboard, and it would get transferred over the wire to somewhere else and get printed just like an actual typewriter would. And then the other person could do the same thing in reverse to send me a message back. So this structure right here really had a huge influence on how people interact with computers, because the first like real interactive computers that were developed, this was how you interacted with them. You literally took one of these teletype machines and fed it into a computer instead of feeding it to another teletype machine. So all those control characters here at the beginning, making a bell ring or acknowledging that a message was sent or starting a message or all of these other, somewhat nonsensical things today were used to control that teletype machine on the other end and tell it to do stuff. After that, we get into symbols and numbers. Neat thing, if you notice here, most of the numbers and the symbols that they represent are a fixed width apart. It's a little bit different now because the keyboard layouts have changed and characters are on different numbers or different places on the keyboard now. But originally, that's where the keyboard or the symbols on the numbers sat. Kind of the same deal when we get into the letters. So they are all also a fixed width apart. So if you want to capitalize something, you just add a fixed number to it and you get the lowercase version, or vice versa if you subtract. So a couple neat things with how they laid out this layout here to make things efficient for processing text. Another interesting thing that came out of this is sorting by things. So most things, when you like sort, when you pull up Windows Explorer and tell it to sort the files by name or whatever, it actually does it in this order, not necessarily in strict alphabetical order. You sometimes hear it referred to as ASCII-betical order, because it will sort all of your symbols first, and then your numbers, and then your capital letters, and then your lowercase letters with all the appropriate symbols mixed in between, because it's actually sorting based on the number that underlies each letter. So after we established this and computers started getting to be more of a thing worldwide, we needed more stuff to be able to print, like accented letters and other symbol-y things. So extended ASCII came out. It started here in the US, where added a few accented letters, added some more like currency symbols and other handy things like box drawing characters, which we'll talk about a little bit later. You could actually draw like boxes on the screen with corners and lines and stuff. So that worked well for us in the United States. Other people in other countries needed different symbols, so they developed their own extension. So key here that I haven't actually said yet. So the original ASCII standard was 7 bits wide, right? A byte, which is what most computers at the time used for everything, is 8 bits. So we had this extra bit that we could use for things. So that's what this is. It's using those extra 128 characters for other useful stuff. Eventually, as this evolved, there were over 220 different standards for what those extra 128 characters could be, right? Depending on where that file originated and who made it and all that kind of stuff. So there are lots of issues with, people sending stuff back and forth where they were using different, what we called code pages, right? Eventually, some people figured out how, or designed a way to embed, okay, I'm using this code page in this text file, so you know which one it's supposed to be, right? But even that wasn't a great solution. So, what was this? In the late 90s, I think, people started working on the Unicode standard, which has sort of evolved into the way that we all deal with text now. The first little bit is actually the same as the ASCII standard. The first 100, or the first byte, basically, is the same as the original ASCII standard and the usual US extended ASCII code page. But the full Unicode standard calls for 4 bytes per character, which in theory means that we have about 4 trillion different little things we can print on the screen. The current standard actually only uses 21, that should say bits, not bytes. Oops. 21 bytes is considerably more. 21 bits, which gives us about 1.1 million characters that we can use. 143,000 characters have been officially defined so far. I think the last revision to the standard was in March. But this includes everything from every accented letter from every language that uses the Roman alphabet or anything even remotely close to it. This includes every character that you need to write in like Chinese and Japanese and Korean and languages that use more like ideogram kind of things rather than just letters. This includes made up languages like the Elvish script out of Lord of the Rings has a place in the Unicode standard. This includes all of the emojis that we all use every day. Every one of them has a place in this thing. So this is sort of the all-encompassing worldwide everything, one big standard that everybody can use for every single piece of communication ever is the idea here. So trade-off here, obviously, 4 bytes is a lot more than the 1 byte that you need to store an ASCII character. So a couple different ways that we can actually store this information. So 3 big standard implementations. There's UTF-8, which primarily is just the 1 byte characters that you'd see in ASCII. In fact, if you open up a UTF-8 file that only has ASCII characters in it, it's going to look pretty much exactly the same as the original ASCII file. Because of the way all of the stuff is laid out inside of the standard, right? Most of the, we call the higher level or the bigger numbered characters have prefixes that you wouldn't normally see in regular ASCII characters. So if you see one of those, it gets interpreted as a multi-byte sequence rather than just 1 byte. The UTF-16 standard does something similar, except every character is basically 2 bytes wide instead of 1. It's not super commonly used, but it's out there some. And then UTF-32 is the full-on, every character is 4 bytes wide. We don't need to do any magic or thinking or anything to process it. So that is chapter 20 in a nutshell. Any questions or comments? I take that as a no. Moving on, chapter 21. So this chapter kind of threw a bunch of stuff at you at the same time because it's all sort of mixed together in how computers are actually laid out and how all of the different pieces talk to each other. So it starts off with this idea of a bus, which we've talked about a little bit before, but it's basically a distinct set of connections and a standard for how the control signals and data within a computer kind of get routed, implemented in hardware. So this is like USB is the universal serial bus. It is a definition not only of sort of the signal that goes across it, but it's a standard of how the hardware actually connects to different hardware. So this is a slightly more, shall we say, modern version of what the book is talking about here. So we have lots and lots of different buses that make up our usual computer structure here. All of this basically lives on your computer's motherboard. It's basically a big circuit board that acts as the bus that connects everything else. So we have a couple of different buses going on here. We have from the CPU to this other chip called the North Bridge, which handles some of basically the routing between different high-speed components on your computer. So your memory and like your graphics card and other things that need to talk very, very quickly to your memory or your processor. So this chip in and of itself kind of acts like the traffic cop for the bus here, right? Another bus that connects the North Bridge to another chip called the South Bridge, which handles all of the slower input and output stuff. So this connects to slower expansion cards inside your computer and all of like your hard drives and your USB connectors and your network and all these other slightly out of date connections that you use to plug stuff into your computer with. One key thing that got brought up here is the idea of tri-state logic. So a connection or a pin on an integrated circuit or something like that, that can either be on or off or none of the above. So if you want to think about it this way, to make a tri-state or gate pretty simply, right? So we have over here, this our voltage. This goes through a switch. That goes through a switch. Okay, so this would be a tri-state OR gate, essentially. Actually, I need one more component here. A very, very big resistor in the middle. You remember earlier from when we were starting to talk about the electronic side of things, a resistor basically resists the flow of electricity. So there's some slightly more complicated electronicsy bits going on here in a real thing, but this gets the idea across anyway. So when one of these switches gets pressed, we have, when this switch gets pressed, we have this complete circuit going on, right? And actually, I made another oops. That should not go. Nope, add. Wrong tool. That should not go there. That should really go to That's the wrong color, but I don't care. To our ground. So and actually I made another, oops, that should have another switch in it. Because we need to be able to control whether this thing is turned on or not, whether it's connected or not. So when this gets disconnected, when we're not pushing either of the OR gate switches, basically, this controls what the value of the circuit is. So if this is turned off and there's no connection back to the ground, this is effectively connected to nothing, which means any signals coming into it don't go anywhere. So this is important for a bus because all of these different components are connected together, right? There's outputs and inputs from different chips all connected in parallel to each other through this bus, which means like if more than one of them are turned on at the same time or turned off at the same time, you're going to get weird, funny electrical things happening because current's going to be flowing from one place to another that it's really probably shouldn't be. So your voltages are going to be off different places. So by having this way to completely isolate your output or your input from the bus, we can actually still share that one big connection, but we have to be a little bit careful about, whether I should be whether I, as one of the chips on that bus, should be sending data or not. Next big thing we talked about, memory. So we've kind of seen this already. This just takes it to the next level. So memory in modern computers looks like this, right? If you've taken apart a computer, you've probably seen one of these before. So this is a memory stick. You'll notice there are 8 chips on this thing. So just like when we started talking about memory a long time ago, or it seems like a long time ago, usually we have, for example, if we have a computer that is primarily like an 8-bit machine, 7, 8, there we go. So each one of these chips pushes out 1 bit at a time, right? And then we have an address input that gets shared across all of the chips. Like this. So let's say each one of these chips can hold 24 bits. When that all comes out, we still have 8 bits, because again, each one of these holds 1024 individual bits, and we have 8 separate chips, so we get 8 bits out. So if we take this structure and duplicate it a few times, I really wish Control A and Delete worked on this program. Super handy. So we have this this 1024 times 8 doohickey, and let's say we have 4 of these. So our address gets sort of split up into 2 pieces because we'll now have a longer address. So this part is the chip address. So this is our old address from before. Over here, we'll call this, for now, the select address. So this part that part gets fed into this thing. This part also gets fed into this thing. So this is we also need lines going there, and I have drawn myself into a box. There. There. Basically. So this determines which chip is going to answer the request for memory, right? And then this part tells it what address inside of that chip to go use. So on a modern memory chip, we do that again, except even bigger. So our address, it's split into 3. So we still have the internal chip address. We have the, call this a bank address. And we'll call this even the stick address, because in most modern computers, you have a place to put more than one actual physical piece of RAM in, right? So this part will go figure out which stick you're referencing. This part picks out which bank on that stick you're talking to. And then this one goes and talks to the individual little pieces of that memory bank to have it feed out the appropriately sized piece of data, right? So, other important memory concept, the difference between static and dynamic RAM. Everything we've seen so far has been what's called static RAM. It's a much simpler circuit, but it's a little bigger and more complicated in the sense of like the actual circuit itself is more complicated. So this mostly gets used inside of things nowadays. Like all of the registers and stuff inside your processor are all implemented static RAM with 4 transistors to a bit. Dynamic RAM, which is, what your actual RAM sticks are using, much simpler to, or much smaller to construct, because thanks to modern physics-y magic, we can store data with only 1 transistor for every bit, which makes the individual memory part a lot smaller. However, the support around it gets a little bit more complicated. So we have to do things like go and refresh the value in the circuit every once in a while. We have to give it a little extra power occasionally to keep that value there. So a little bit more complicated on the support side, but smaller and cheaper to actually go construct. Next thing we talked about, video. So actually getting a useful display out of a computer. Even though all of our modern displays are all digital and we don't have to worry about things like giant bulky CRT tubes and scan lines and all of these other fun things that we had to think about back in the early days of television and computers and stuff. Everything basically still works the same way. It's basically your computer is sending out a single stream of bits that represent all of the individual pixels on your screen, as well as some data about what resolution or what size it thinks that the monitor is acting like. And the monitor then interprets that and changes the individual pixels as it goes across. So there's still kind of a virtual scan line process going on, even inside of our modern digital electronic monitors. So I'm not going to get into the details of that here because it's not super relevant anymore, but that's kind of the idea of how memory or how video works. You dump all of this data that describes the colors and patterns you want showing up into a piece of memory somewhere, and then your video card goes and reads that memory and spits it out to the monitors appropriately. we talked a little bit about how keyboards work. So modern keyboards are not just simple, every key has an individual switch that has an individual connection back to a circuit somewhere. It's a little bit smarter than that. There's two different ways to run a keyboard. The one that the book talked about is a little bit more complex. It basically involves having a clock, having an oscillator that goes through and checks different groups of keys and figures out which one of those out of those group is pressed at any given moment, and just does that very, 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 very quickly. There's some advantages to doing it that way, but it's a little bit more complicated to build and complicated to implement. So most keyboards anymore look something a little bit more like this diagram right here, where every individual key is basically connected to two separate lines of power and lines of input. So we basically form what's called a key matrix. So when you push a key, it actually turns on two different inputs on a circuit that typically lives inside of your keyboard. And based on which two inputs got turned on, it figures out which key you're pressing and uses that to determine which code to actually send down the wire into your computer. It also talks about the idea of interrupts, which we'll talk about again here in a second when we get into operating system stuff. And the last thing this chapter talked about is storage. So back in the days of floppy disks and tape drives and actual spinning hard drives, got into the details of how those kind of worked. They're all kind of fundamentally the same idea. We are taking some medium, whether it's magnetic tape or a spinning magnetic disk thing, and encoding values into that medium with a little thing that will either magnetize or demagnetize whatever it's looking at right now. So I actually have, from when we were cleaning out a retiring teacher's classroom, actually have here a disassembled 1980s era hard drive that I made my way home with. So you can see here, we've got several magnetic disk things that spin around very nicely. Most modern hard drives like this spin at several thousand, actually tens of thousands of RPM, so pretty darn fast. This piece right here actually can move across the surface of the disk to read different parts of it. And then you probably can't see it real well from this angle, but there are actually units like this attached to every one of the 4 disks that are in here. So kind of like the RAM, we can read essentially 4 bits at a time out of this thing, because each one of the heads that are pointing to the disks can be reading at the same time. And then on this side, on the back here, you can actually see the connector where it plugged into the computer. It's these things right here. It actually connected more like a modern PCI card or something like that, where it fits into a slot physically in the computer. And then here's the power connector. So, but these things basically, again, all kind of work the same. They basically give you a continuous feed of bits out of the thing, and then it's up to software inside of the computer to actually make sense of what those bits are, and also to tell these things where to go read and write from on the disk. The second thing underneath the floppies here, you probably haven't ever actually seen. This is a tape drive. So they're starting to get less and less common. People are really beginning to replace these things, but they're still fairly popular, very much used in big enterprise systems for backups. Not so much for like data you're actually using on a day-to-day basis, but the downside to these things is if you've ever used a cassette tape or a VCR to watch videos, you know that if you want to go to a specific spot on, on the song or on the movie or whatever, you have to actually sit and rewind or fast forward. And it's a fairly interactive and somewhat time intense process to do that, right? You can't just say, oh, go jump to this spot. You have to actually go find it on the tape. So this kind of suffers from the same problem. You can tell it to go to a certain spot on the tape, but it has to mechanically go work its way through the tape to find the right spot. So it's good for if you're just dumping data in or pulling a whole bunch of data out, but if you just want to go grab something, it takes a little longer. So it's very much falling out of fashion anymore, but still very much in use. So that is the end of chapter 21. Any other questions about any of the myriad of topics that came out of this one? Memory cards and internal hard drives different in what they store. All right, question from the chat. How do memory cards and internal like spinny drives differ in how they store things or what they're storing? So most memory cards and flash drives and solid state drives basically are all the same technology. They are using subatomic physics magic basically to instead of using a moving magnetic medium to encode data, it's actually like solid state. It's all transistors inside, right? That somehow through the magic of physics actually persist data inside of them without power still being connected. So at a high level, they all work the same way, right? Because they're basically just saying, the computer says, hey, give me this many bytes from this address, and then the drive goes and hands that data back. So at a high level, they all work the same. It's the low level, how the data is actually stored physically, that they work a little bit differently. All right. So moving on to the next topic, chapter 22, operating systems. Oops. So the job of the operating system in a computer is basically to handle a bunch of the low-level, complicated, annoying garbage that you would have to deal with otherwise, and make it a lot easier for programmers to write software as well as for people to actually, use the computer. So big important things that an operating system should do. First important thing is actually the process of booting the computer. So like the book talked about, if you just turn on a computer without going through some sort of process to clean things up and start with a fresh slate, all of your memory is going to be full of random garbage, and it's going to start going through and trying to execute some of that stuff like a program, which probably is harmless unless you accidentally tell your hard drive to go erase itself or something. So we don't want to do that. We want to start off in a consistent, easily used state. So part of that process is having a base piece of software that kind of goes through, erases all the RAM, sets everything up in a clean slate, and starts up a piece of software that lets you actually interact with the computer and do useful things. Other important thing, providing some sort of file system for simpler access to all of your data. So rather than just having a big stream of data coming out at you, the operating system puts a layer on top of that where you can ask for, okay, I want a file called X. Go give me the contents. And the operating system has mechanisms inside of it that we call file systems to say, okay, they asked for this file. It starts at this address on this drive. It's this big. It also has pieces that live over here and over there and over there. And then it goes and grabs all of the pieces and puts them together in the right order and hands it off to the program in one nice, happy little package, right? Another important thing, providing some sort of like utility software and what we call a shell, or the actual interface that you use to interact with the computer, whether that's, pretty graphical Windowsy interface or just a command line interface where you're typing commands in and making the computer do stuff that way. Usually that's fairly tightly coupled with your operating system, as well as, again, simple utility software like, text, excuse me, or text editors or Paint or Minesweeper or things like that. Just simple things that come with the computer, help you figure out how it works or do very basic, simple tasks with the computer. The last thing the operating system does, big and important, is basically handling, running and allocating resources for and providing access to lower level hardware things to all of the programs that are running on it. So the operating system is the thing that goes, okay, we're going to start running this program. It needs a hunk of memory, and it needs access to files, and it needs access to the video card, and this and that and the other, and provides easy access to all of those things in a slightly more straightforward fashion than just having to go poke at all of the individual pieces of hardware manually. A couple other important things that got mentioned in this chapter: the BIOS, or the basic input and output system, basically a low-level interface to all of the hardware inside of the computer. So BIOS, which if we jump back to the architecture picture from earlier. So BIOS sits down here and is very closely connected to all of the like I/O devices, so your keyboard and your mouse and some of the other things that do basic slower input and output from people, not necessarily other computers. It basically helps deal with getting all of those things fed into the computer in a way that the computer will understand a little easier and have access to that data that's coming in, getting things put in the right place in memory, that kind of stuff. Another big important thing I mentioned a minute ago is the idea of interrupts. So these are basically processor flags that can get set by other pieces of hardware inside the computer that tell the processor to stop what it's doing right this second, put that off to the side, and go deal with this other thing, like right now. So every time you push a key on your keyboard, it fires off an interrupt to tell the CPU to go grab the key that you pressed and shove it into memory somewhere. Every time you move the mouse, it does the same thing. It tells the CPU to stop, go grab the new coordinates or the relative movement that the mouse did, and go put that in memory somewhere so the operating system can go grab it. Every time that your network card gets a packet from the internet, it fires off an interrupt and tells the CPU to go grab the contents or the data that you got out of the network card's memory and go put it somewhere else so that the operating system and everything can get to it. So, which then leads back to the idea of the operating system kind of managing some of this process and handling, all right, I got told to stop doing what I'm doing, so I need to be able to have a place for all of that stuff that I was doing to go live off to the side somewhere where I go deal with this other thing, and then very quickly go get back, load in the stuff that I just unloaded, and keep going. Likewise, in modern operating systems where we can have, 30 different programs running at the same time, the operating system is responsible for like scheduling how much time each one of those programs gets to run on the processor, and then kicking it off, storing all of the stuff somewhere, figuring out what the next thing to go run is, and bringing all of its resources back online and running it for a while, and jumping to the next program, and jumping to the next program, on and on and on, forever and ever and ever. CP/M is mentioned in here, and we got a little lesson in how to actually use it. This was the first big commercially viable operating system out there. So again, the book kind of went into how you actually use it. You will notice if you've used like the Windows command line before, like the DOS prompt, basically, it's very, very similar because CP/M very much inspired how the original DOS implementation worked, which then inspired how MS-DOS, you know, Microsoft's big first product that they came out with, which then influenced all the rest of development of Windows and everything else that Microsoft has done since. So this is sort of the root of modern computing in a lot of ways. So, any questions, comments there? No? Moving on. So, chapter 23 talks about floating point numbers. Spent a lot of time talking about what is ultimately a fairly simple concept. Talked about one other way that computers can store numbers, BCD, binary coded decimal. I don't think anything really does that anymore. Basically, instead of actually encoding a number just straight as binary, you actually encode each individual digit in the number as 4 bits and build a number out that way. It does have some utility and some usefulness to it. It's slightly simpler to, you know, do digit-based math very precisely, but it's space inefficient and kind of gross, so it doesn't get used a whole lot anymore. Floating point numbers, on the other hand, are everywhere. Anytime that you have, you know, really, really big numbers or really, really small numbers, this is typically how your computer is going to store it. So ordinarily, the way we've been talking about numbers, if you want to store a really, really big number, you need a really, really big amount of memory to store it in. But we can kind of cheat a little bit if we're willing to give up some precision in our number that we're storing. So basically, we use scientific notation. So this is the standard for what we call a single precision floating point number. So this is 32 bits. And each one of those bits gets used for something a little bit different. So we have 1 bit for a sign, whether it's positive or negative. We have 8 bits for an exponent, is used here. Then 23 bits for what they call the mantissa, or the base number here. So the number gets stored basically in scientific notation. We have a number times 10 to a power. So you'll note, if our base number here is bigger than 23 bits, then we may end up losing some precision. Also, this isn't stored just directly as a number like this. It's stored in a slightly convoluted way that it's encoded into binary. So there are actually some numbers that you cannot represent this way because the math just kind of doesn't work out. There was a long-standing bug in Excel. I think it got fixed sometime in the late 2000s, where I forget exactly what it was, but if you added 2 like simple numbers together, it wasn't actually 2 plus 2, but it was something kind of along those lines, right? It would come out as not quite right, like it was going to come out as 4.0000002 or something like that, because they weren't quite handling this correctly. So it's kind of one of those trade-off things. We're able to store humongous numbers this way, but again, we kind of lose a little bit of precision in that conversion. So hot tip, whenever you're programming things that have to do with money, don't store your money as floating point numbers, or you're going to be losing pennies every now and then, and it causes problems. So, any questions about that? Nope, moving on. So, chapter 24, we start talking about actual like programming, not just sort of hand assembling our software and punching it in with flipping switches and putting things into memory, but how do we write slightly easier to understand code and have the computer do the hard work of figuring out how to translate it into something that the computer can actually understand. So a couple key concepts, one of which the book didn't exactly mention. The idea of a compiler, a program that takes in some sort of human readable code and reads it, figures out what to do with it, and turns it into machine code. So the first thing you do when you're designing a new programming language, basically, is you go write the compiler. You write the thing that's going to turn your programming language down into machine code. Sometimes that's a several step process where you take your code and you turn it into something else that's a little bit closer to machine code that you can then use another piece of software that maybe somebody else has already written to do the really low level stuff. Like Java, yes, exactly like Java, where the actual Java compiler is sort of, it combines a compiler and an interpreter, right? So in Java, the actual Java compiler turns it into this intermediate state. They have a word for it that's not coming to mind at the moment, but it's basically bytecode. That's the word they use for it. So it's not machine code, but it's also not human readable Java anymore either. And then when you install Java on your computer, what you're actually installing is a Java interpreter that runs that can read that bytecode and turn it into machine code and then go do it. So yeah, an interpreter is just a compiler that runs in real time instead of dumping out a program file, right? And then the book talks about assemblers, which is still a word that gets used now, but it's basically just a compiler for assembly. So instead of, like we've been doing, or at least hypothetically doing, where we've been hand assembling our programs, writing out the assembly, and then doing the conversion to the actual binary representation that the computer is going to read, the computer does that part for you. Talks about a couple of very early programming languages, ALGOL and Fortran and Pascal and C, gives a few examples of some of those, and talks about the idea of a high level versus a low level programming language. So a low level programming language, something like assembly, where it's very, very close to what the machine is actually doing, excuse me, versus a high level programming language where the computer takes care of a lot more of all of the nitty gritty details. So you don't have to think as much about what the computer is actually doing, and you can focus on like the actual problem that you're trying to solve, right? In the early days, this was sort of a very binary sort of thing, right? You had assembly was pretty much the low level language, and everything else was kind of a high level language. Like C was considered a very high level language in the 70s because you didn't have to worry about manually jumping around in memory to run code and stuff like that. But as we've evolved and as people have made more and more programming languages and made it easier to get into programming, it's become a lot less of a binary thing and evolved into more of a spectrum of here's the low level stuff all the way up through your high level, very easy to use kind of stuff, right? Yeah, and then the rest of that chapter was just some examples of what I think mostly what ALGOL, one of the earlier high-level languages, kind of looked like. So, any questions there? No? Cool. Then the last chapter gets into how computers actually do graphic-y stuff and sort of a little bit of the evolution of how we got from black monitors with monochrome text sprawled across it to this, right? So sort of the evolution of how people interacted with computers. So we started off, the very first computers were what we call batch processors. They weren't interactive at all. You'd dump in your deck of punched cards with your program on it or whatever. You turn the machine on, it goes through your cards, it goes and runs your program, does whatever you told it to do, spits out some more cards or a printed result somewhere, and then it stops and you turn it off. And then you load in the next thing and then you repeat that cycle over and over again. There's no interactivity to it at all. After that, this was, I think, the early mid 70s where we started hooking up these teletypewriter doohickeys I talked about earlier, started plugging those into computers. This also brought across the idea of time sharing, like I talked about in the operating system thing, where part of the operating system's job is to divide up the time that programs get to run, right? So you could actually like interact with the program as it was running. You could do things like have your program ask you questions as it's running, or interactively get data from you, or things like that. After that, we got to video teletypewriters, essentially, where we weren't printing the output on paper anymore. We were actually getting a display of stuff, right? So you'd have an actual monitor with a keyboard that would be attached to some big mainframe somewhere else to actually go do all of the work. Eventually, along with the development of like personal computers, this got into the internal structure was kind of all the same, but we still had this idea of I have this teletypewriter or a teletypewriter emulator, a thing that acts like a teletypewriter with a keyboard and a screen that is attached to my little computer. Since the connection between things was a lot faster and we could do a lot more interactivity, this let us start doing things like, you know, colors on the screen and moving the cursor around to draw boxes and stuff, which then made it a lot more interactive to use. The big killer thing that made the personal computer revolution really take off, especially in businesses, was this lovely little spreadsheet program called VisiCalc. This was the first digital spreadsheet that existed, was written for the Apple II personal computer in 1979. So this is really kicked off the personal computing revolution, right? It was an easy to use, like a regular person without a whole lot of special training could come up, punch some numbers in, punch in some very simple like mathy things, and have automated calculations and all of the other good stuff that comes along with very simple spreadsheets. So that, the whole personal computer revolution, along with some contributions from a company that none of you probably think of as having anything to do with computers, Xerox, you know, the copier people, really, because this was where the idea of a graphical user interface came from, like Windows and a mouse and all of that good stuff. The mouse actually came from somewhere else. I think it was MIT, Doug Engelbart in the late 60s. But the idea of actually having windows and things you can drag around and interact with on the screen came out of Xerox PARC Research Center out in California in the 70s. So the Xerox Alto was the first like graphical interface computer out there. So the idea was the screen was like the equivalent of a piece of paper. It's all portrait instead of landscape, which is still weird today. But this was the actual computer. This bottom cart thing that it's sitting on is the actual computer that it used to do all of the stuff. You have your keyboard, you have your mouse, and you know, you could start programs that lived in Windows and you could drag those windows around and you know, all that kind of cool stuff. What ended up happening here, Xerox never really tried to sell a lot of this stuff. So as people came and went and technology companies kind of started growing and started swapping people around as people started looking for new jobs, a lot of these ideas went over to Apple, which kind of borrowed a lot of these ideas for the Apple I and Apple II which again kind of kicked off the personal computer revolution. And Microsoft sort of glommed on to a bunch of those ideas. And then we got Windows in the late 80s, and everything has kind of exploded from there. So that is the end. Oops. There we go. So that's it. We're done. Any last questions, parting thoughts? Nothing at all. All right. Well, it's been fun. Maybe we'll do another one of these in a couple weeks. James says this was cool. Yay. So, I guess I will see everybody when I eventually start doing the next book.